Okay, so how's it going? Again, I hope you didn't spend too much time on these problems. I don't think there's any problems exactly like this on the quiz, but I still think they're kind of worth our time. So let me run through this super duper fast. If you had a function that was shown graphically like this rather than from a function rule, could you find the domain of f? I believe you could. You guys know the domain is just going to be the set of valid x inputs, which pretty obviously for f runs from -6 to 6. So the domain of just f is -6 to 6, which I think is child's play for most of y'all by now. What's the domain of g? Well, obviously it starts at -3, goes all the way to 9. So the domain of just g with no operations associated is -3 to 9. Okay, great. Good news. The sum function, the difference function, the quotient function, they'll all have the same domain, and they will all have a domain that is just the intersection of these other two domains. And more good news, finding the intersection visually is very easy. You literally just look for where the two graphs both exist at the same time. And so the blue starts here, but the red ends here. So of course the intersection would be right there. The intersection would run from -3 to 6. So the domain of all of those, all three of these, is -3 to 6. Okay, getting into slightly more interesting territory. We've got the quotients, and these quotient functions have domains that are just the intersections of the domains. So taking this previous domain as a starting point is not a bad idea. Our domain should just also be -3 to 6, but there will typically be a few more restrictions because you have to restrict the zeros of the denominator. So if our denominator is g, and if g is the blue function, then I can see that the blue function has a 0 here at -2, and there's another 0 here at 6. So the -2 is definitely firmly in this. There's my dog. Check out my dog. He's awesome. The -2 is in our interval, so we've definitely got to slice that out. We'll go -3 to -2, soft bracket. Then we can start again from -2 and keep going. But when we get to the 6, that guy can't be included anymore. So the hard bracket that used to be at 6 is now a soft bracket. But that would now be the domain for f over g. Yeah, dog settled down. Good for him. Let's do lavender now. And let's do the other quotient function where this time function f is in the denominator. And again, I would take as my starting point the intersection of the two domains, which is -3 to 6. But this time I need to cut away any zeros of my denominator, but my denominator is now function f. And function f is red. So when does the red function equal 0? And this is a little more complicated. We can see that function f has a 0 here at -4.5. Then it's also got a whole interval of x values that are zeros. So I need to cut all that away. Or do I? The -4.5 is outside of this window anyway. So that 0 is a moot point because it wasn't in the intersection anyway. The intersection started at -3. But the intersection runs all the way to 6. And so we can see we need to cut out this whole interval actually. So we will now go from -3 up to +3. And I can't include +3 because that's a 0. Then I won't pick up again until 5. And I won't include 5 because that would be division by 0 again. And from 5 I'll go all the way to 6. And 6 is a-okay. So there is your domain for g over f. All right. And then finally, the compositions, which I think is what's been given most people the most headaches. But for the composition, now's a good time to remind you, by the way, that I don't think there are questions like this. I don't think there's a question where you have to do the domain from the graphs. but you do have to do the domains from the function rules. So you might want to see the previous video that I posted. I included a couple practice problems for that, literally a couple, like I did one. And then I talked about another option. So there's really only sort of 2 problems there. But check your packet has more. Okay, so what are we doing now? We're doing F composed with G. So if you're doing F composed with G, then for the first time, the intersection of the 2 domains from before, that's not our starting point anymore. Our starting point is to just make sure we satisfy the inner function, which is G. So we take as our starting point the domain of G, which is -3 to 9. Then from there, we have to make sure that none of the inputs go into G and then turn into outputs that can't be plugged into F. So let's think about F. What does F accept? F will only accept values that go from -6 to 6. So that's the domain of F. But the domain of F is my inputs, and the inputs of F are the outputs of G. So let's make sure those things play together. Who's in the set of outputs, the range of G? G is the blue function, so it goes from -3 to 4. Which I guess means I can happily report that literally all the outputs of function G are valid inputs for function F, because F would take anything from -6 all the way to 6. And the only outputs we get from G go from -3 to 4. So those outputs are fully contained by the domain of F, which means my initially restricted domain does not need to be restricted any further. This is the domain. This is the quote-unquote easy one. And I'm pretty sure I set this up that if we do the other domain, it's going to be a lot more challenging. So let me make some room for that. And I don't know. Let's see how this goes. Make a little dividing line. We'll start again. So we are now doing G composed with F, which means you'll take as your first set of restrictions, you'll start with F. F goes from -6 to 6. So certainly nothing outside of this window can possibly be in the domain of our composition. But now what? Now we got to actually think about, hey, what does F spit out? So what's the range of F? And the range of F was the red function. That goes from -5 all the way to 3. However, the outer function G's domain says, very politely, that it will only accept values from -3 to 9. And so if we get outputs that go all the way from -5 to 3, then there are going to be some values in the range of F that are not in the domain of G, because G will only accept things that are bigger than -3, which means we need another horizontal line. We need it at -3. And visually we can see that this entire section of function F that dips below this line, those guys are all bad, because all of those outputs, like -5, if you tried to evaluate function G, the blue function, at -5, the blue function doesn't exist there. We would be undefined. Or here, at -4, if you tried to evaluate there, the blue function hasn't started yet. We would be undefined. So I need to cut away any x value that returns a value less than -3, which means this whole interval needs to get cut away. So who's the good stuff then? Well, basically you just have to be in the domain of the red function. That would mean -6, and then we're good. But once we get to -3, -3 maps onto -3, and so that point's fine, but anything beyond that now we're getting values that are too small, until we get to 0. And then 0 maps onto -3, and then that's fine. And then we're good until the red function ends at 6. So there, all that red stuff should be our domain of our composition. It should be -6, to -3, and then union 0 to 6. So that's one problem down, and I gave you guys 3. So we'll go through the other 2. Maybe a little bit faster, with less explanation. Alright, so what's this going to be? Obviously, I think the domains of f and g are pretty self-explanatory, so I'm going to do that very fast. Domain of f is -7 to 5. Domain of g is -13 all the way to 11. Again, we're going to just lump all 3 of these guys together because we know that all 3 of these basic operations all have the same domain, and that domain is just the intersection of the 2 previous domains. So these orange guys will all have a domain of, we can see that function g fully contains function f, so that means the intersection will just be the domain of f, which is -7 to 5. And that was on purpose for this one. Alright, now we've got a quotient function, which means my domain should be the intersection of the 2 domains, which we said is in this case is just the domain of f, so -7 to 5. But then you must take away any zeros of the denominator. So function g, he sure has a lot of zeros. -8 is a 0, and this whole interval is zeros. So we saw that in the last problem. We saw this exact same thing in the last problem, that there was a whole interval of zeros that had to be cut out. So we're doing this same concept. The -8 is even the same, where you've got another 0, but it's outside of our little window of restrictions already. So this -8 doesn't represent a new restriction. He's already been cut away because he's not even in our intersection. But when we cut away this flat spot, we end up going from -7 up to -3. No -3 allowed because it'll be 0 and will be undefined. And then we can't start again until 3. Not including 3, up to 5. And that should be green, like its friend. Alright, so there's one. Said I was going to go fast, so here I go. Now this lavender one. Let's do g over f. Again, you're going to start with the intersection, so -7 to 5. Now this one's a smidge different because this time it's function f that I don't want to ever equal 0. And very on purpose, I kicked this one up until there was just this one little baby 0, just the 5. If I kicked this up by, one more, it could potentially have no zeros, and then you would have no further restrictions at all. That's possible. But we do have the one restriction at just 5, which means this is another one of these ones where all I really have to do is turn the hard bracket into a soft bracket. Just the 5 is not allowed in the domain of our quotient. So there's another one for you. That one happened. Now we can do the compositions. Red, orange, let's use this weird puke yellow color, and we'll do f composed with g. Alright, as I said in the last one, you're going to start by considering the domain of g, which is this big domain that goes all the way from -13 to 11. Now you're going to take out any more values of x if g maps onto values that are not in the domain, or not in the domain of f. I said that right. So basically you want to consider the range of g. Think about who does g map onto, and g has a min of -6, and g has a max of only 1. So it's got this wide domain, but a relatively skinny range. Now what's the domain of f? What values will f actually accept? F will accept values from -7 to 5. So guess what? If I'm only getting values from -6 to 1, all of that lives inside of this guy's domain. So this is another one of these examples that doesn't need any further restrictions beyond just satisfying the domain of the inner function. Am I going to sit like this? My head looks weird. See my head over here? I'm like creeping. Whatever. You guys don't care. Neither do I. Maybe you care. There I am. Okay, I hope you understand. Let's do the last one with just gray. We'll do it in gray. So this time G composed with F. So what's the deal? Satisfy the inner function first, so -7 to 5 would be our acceptable domain. Then again, if I'm thinking this through, let's think about the outputs of F, meaning the range of F. F's got a range that goes from 0 up to 8. Are any of those values no good for the domain of G? Well, G's got that huge domain, right? -13 all the way to... I thought I set this up, though, that some of these were bad. I guess not. Maybe I screwed up. -13 all the way to 11. I'm not screwing up, am I? I thought I set this up to have some further restrictions, but maybe we don't. According to this, everybody in the range of F falls in the domain of G, so there would not need to be any further restrictions again. That's kind of a boring one when it comes to the compositions. The quotients were sort of interesting to think about, though, I guess. They can't all be super challenging ones. 7 to 5. Yeah, okay. And then... yeah, alright, whatever. I think I did that right. So this is the last one. I'll do this one for you quickly and then we'll let you go. F is red. So the domain of F is obviously -6 to 6. Well, I guess I didn't even change that. That's the same as the first one, right? Yeah, alright, my bad. And the domain of G is -10 to 2. Sum, difference, product, all the same. They're all just going to be the intersection of these. We can see that the things they share begin here and end here. So -6 to 2. So that's the intersection. That intersection is important as we consider our quotient function, because we'll take that as our starting point, the -6 to 2. And as we've already said twice now, the only further restrictions are the zeros of the denominator, which is function g, which is blue. So no -9s and no -1s. And again, -9 is outside of this window anyway, so it's only the -1 that we need to exclude. So we will go -6 to -1, soft bracket union, -1 to 2, hard bracket. There's your domain for that quotient. Then you've got the second quotient function, whose domain will certainly be the two intersections, -6 to 2. You've got to be in the intersection or else you're out. Then we have to also restrict the zeros of function f. Function f has two zeros, the -3 and 0, and both of those lie in here. So, you know, I haven't been doing this, but you certainly can just do the set subtraction thing. And when there's two restrictions, you probably want to do this. So -3 is restricted, and so is 0. If you really want to just keep doing it as the union of separate intervals, you could. So you'd go -6 up to the -3, soft bracket union. Then you'll go -3 up to 0, soft bracket union. Then you'll go 0 to 2. But I mean, seeing these things side to side, you can see why my preference is to use the set subtraction. It takes a lot fewer characters to just do it as a set subtraction problem. By the way, of course, we could be doing that up here too, just subtracting just the singleton value -1. And that's a perfectly valid way to express that answer. Okay, let's do the two compositions that hopefully I came up with something interesting this time. So fog. Why do I keep doing that? Bothers me when you guys do it. Why do I keep doing it? All right, for fog, I just did it again. Start with G, negative 10 to 2, yeah. Then check and see. Are there any outputs from G that are not in the domain of F? Well, the domain of F starts at negative 6, so we're definitely clear in that regard. Negative 6 is way down here. And no, function G never dips below negative 6. But the other limit is positive. Well, I guess I shouldn't be saying but. The other limit on the domain of F is positive 6, and if you look up here at positive 6, then no, function G stays under that line. So this is kind of a good way to visualize this too, is we can see that none of the outputs of G go below the minimum value for F, and none of them go above the maximum values for F. So this is another problem where we don't need any more restrictions. All right, I'm going to be pretty upset with myself if this next one isn't more interesting. So G composed with F. You'll start by taking the domain of F, which is negative 6 to 6. Right, it's the red one. Negative 6 to 6. Now let's do this again, trying to visualize this with the sort of lines. I still think that's the best way to do this, honestly. All right, so function G. Function G doesn't want any values less than 10 or negative 10. We're clearly not getting that. Negative 10 is way down here. But function G doesn't want any values greater than 2 either. And suddenly, now we see that there is a whole interval on which function F does give us values that are greater than 2. So this whole wing right here is bad. So we can see that starting here, we'd need to start restricting x values. So even though function F goes from negative 6 all the way to 6, anything greater than 2 gives us y values that are too big to be in the domain of function G. So we'd have to slice that away. So all of this stuff is bad. Now the 2 itself is not bad. 2 maps onto 2, and you can evaluate the blue function G at 2. You would get an output of negative 1. So basically I'm saying we got to go from negative 6 only up to 2, and you can include the 2. So there is a second restriction here. Okay, I'm going to try to keep these videos shorter, so I'm going to stop talking now, and I'm going to post this, and goodbye, good luck.